Okay, today talking about voltage and current division. I'm going to start out with the derivation and motivation for doing this, some formulas, and then a cool life hack you can do if you're stuck, can't remember the formulas in an exam or whatever. So, okay, let's see. Say we're given, for voltage division, a circuit like this. You got to find the output voltage, given some input voltage and some impedance values. So how would you even approach this, first of all? Let's say we're given 15 volt voltage source, 5 kilo ohm and 10 kilo ohm resistors, and we're asked to find the voltage across this 10K resistor here. Well, one thing you can note is that everything is in series, so the current is going to be the same through all the components. So if we just use that to our advantage here, we know that the voltage is the current times resistance from Ohm's law, so the current is V over R. We have 15 volt source divided by the total resistance, which is 15 kilo ohms. We have a 1 milliamp current. So now we can find the voltage across R1 is just I times R1, 1 milliamp, 5 kilo ohms, 5 volts. Similarly, voltage across R2 is just the current through it times its resistance, 1 milliamp, 10 kilo ohms, 10 volts. Let's check that with Ohm's law. 15 volts is the sum of these two voltages, and yeah, that makes sense. 15 is 5 plus 10. But we had to find the current, and we didn't even use it, so that kind of sucks. There's probably an easier way to do that, and there is. If we notice here that V out, or just the voltage across this R2, which we're interested in, we know it's the current times its resistance, but we don't really need the current directly if we know that it's the voltage over the sum of the resistances. We don't actually need to calculate this. If we sub it back in here, we can just say V out is V in times R2 over R1 plus R2. See here, we just moved V in here. I turns into V in over R1 plus R2, and we're done. We can check with our previous result. See 10 volts, which we solved for here, is that equal to the source times 10 over 5 plus 10? Yeah, that checks out. So in general, if we have a complicated circuit like this and we want the voltage across, here we go. We want the voltage across this resistor here, just randomly in the series string. All we need to do is we know that the voltage across the whole combination in series is V in. We multiply that by the resistance in question and divide by the sum of all these added together. So if these are all 1K resistors, we would just have the voltage across this one is V in times 1K over 1, 2, 3, 4, 5, 6, 7, 8, 9K. Now let's look at current division. So let's say we have a situation like this and we want to find the current through all these resistors. Well, that's pretty trivial because we already know the voltage across all of these resistors. See, the nodes here are the same. They're all common to both terminals of the resistors. So the current through R1 is just V in over R1. The current through R2 is just V in over R2, and so on. So the interesting part comes when we are given a current source and then asked the current through each branch here. And so similarly with voltage division, we know that if we know the voltage, we can find the current. So before we had to find the current to know the voltage. Okay, so why don't we do that? We know all resistors are in parallel, voltage is the same across all of them. So if we find the equivalent resistance seen by this current source, we'll have the voltage because we can multiply the equivalent resistance by the current and then get the voltage across everything. So let's do that. We have V equals IR, 15 milliamps, which is our I in, times the equivalent resistance seen. So a quick derivation of the equivalent resistance, you know, from physics class and whatever, that this formula here, 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 if there is a third one here. So if we just take the inverse of each side, we know we have REQ equals 1 over 5 plus 1 over 10. And we'll multiply the right-hand side by 1, which is 5 times 10 over 5 times 10 equals 1. But if we strategically distribute this 5 times 10 to the numerator here, and this 5 times 10 to the denominator here, we see that we have a cool formula here where the equivalent resistance of two parallel resistors is just the product over their sum. So we'll use that here. We have V equals IR, I is 15 milliamps, R is 50 over 15, so these 15s will cancel and we're just left with 50 volts for the equivalent voltage. Now we can find the current through each resistor since we have V and R, so the current through R1 is just 50 volts over 5 kilo ohms is 10 milliamps. Current through R2, 50 volts over 10 kilo ohms is 5 milliamps. And we can check that with KCL. We know that we have 15 milliamps going in. We have 2 currents coming out. So let's see, is 15 equal 5 plus 10? Yep, that does. And okay, KCL checks out, but that also kind of sucked. We had to calculate so much stuff. The voltage, we didn't even use it. And it's such a 3-component circuit, it's so simple. But notice, if we sub in another equation as before for voltage division, we can simplify our problem-solving process. So we know, let's say we're solving for the current through R2, which is here. We'll just call that I2. And we know that's the voltage across it divided by its resistance. We know the voltage is the current into the circuit times the equivalent resistance. Now we have our fancy equation for the equivalent resistance. Now, if we take this here, move it over here, we see that the denominator cancels R2 with this numerator R2, and we're left with just I2 is IN times R1 over R2 plus R1. Similarly, if we're looking at the other branch here of the current through I1, simple equation for that is just IN times R2 over R1 plus R2. And in general, if we're looking for the current through some resistor here, we know that it's just IN times the equivalent resistance seen by this current source divided by the resistor in question. So let's summarize both of those real quick. Here's the voltage division problem. We're looking for the voltage out, we're calling it, which is really just the voltage across this impedance. And we know that that's Vin times the impedance in question over the sum of the impedances in series. And if we're looking for the current through, say, Z1 here, we know it's just the total current seen by the parallel combination times the impedance not in question over the sum. And notice that we have Z's here instead of R's. That's because these actually work for frequency-dependent impedances as well. So the next video I'll have will be about the impedance of capacitors and inductors and stuff. But just keep that in the back of your mind that it also works for that. And now for the life hack, which is if you're in an exam or just at work and you can't quite remember the formulas for voltage division or current division, just use your intuition. Here, if we're looking for V out, we know that it's the voltage across this 2 ohm resistor. And since voltage is proportional to resistance, we know that the voltage across it should be double this here. So even if you're given some circuit with a weird value for voltage and 2 very different resistances, just have a piece of scratch paper and put this exact circuit down. I like to use 12 because it's a multiple of 2, 4, 3, 6. So you'll guarantee to get kind of an easy answer. And then why not use 1 and 2 ohms if it's just a play example anyway. And so let's check, is this equation right? V out is Vin times the top one over the sum. That would give us 4 volts. Well, that's less than half of this. We know they're divided between these two, so it's probably not it, because we know that we would want double the voltage across this one. So let's try again. If V out is the input voltage times the one in question over the sum, we get 8 volts. Okay, maybe that looks good. We have a good amount of voltage drop across this. It's about double this. So if this was 8, that's 4. That gives us the 12 we want, and we're good to go. Similarly for current division, if we know that current is proportional to 1 over the resistance, because current wants the easiest path to flow through. So let's say we want to guess and say, okay, maybe the current through this 1 ohm resistor here is the input times the 1 ohm resistor over the sum. That would give us 4 amps. No, that's less than half here. We know that at least half is going through that if this is a higher resistance. So let's try again. And maybe I1 is IN times the resistance not in question over the sum. We get 8 amps. Okay, that makes sense. We're getting twice. If this was 8, this could be 4. This would be twice. Yeah, that makes sense. Now we're getting back to the 12 we want. So yeah, in conclusion, trust your intuition and stay tuned for another video on complex impedances and frequency dependence.